Chapter 5, Section 2, the natural logarithmic function integration. In the last section we did differentiation, which is going to lead up to the power rule of integration, where we could never integrate if n was -1. Well, now I'm going to show you how we can avoid using the power rule, because the power rule doesn't apply, when we have to integrate x to the -1, or 1 over x. Because it's the reverse of the differentiation rule for the natural log that involves the natural logarithmic function. So here's our theorem, the logarithmic rule for integration. This is one that you're going to use a lot. You use the power rule for integration a lot, you're going to use this one a lot as well. Theorem says, let u be a differentiable function of x. The integral of 1 over x dx is the natural log of the absolute value of x, because we have to make sure that we are not taking the natural log of a negative number, because that's impossible. It's not defined. And then plus c, the natural log of the absolute value of x plus c, and kind of the chain rule here, because if we let u be a differentiable function of x, the integral of 1 over u du, and of course the du has to be there, it has to match up with the u, is equal to the natural log of the absolute value of u plus c. So we're going to do some simple examples here. The very first one I have is going to pretty much use rule 1 here. All I'm going to do is I'm going to toss the 5 out in front. And I'm going to write this so that it looks just like this rule right here, which of course is equal to the natural log of the absolute value of x plus c. So this is 5 times the natural log of the absolute value of x plus c, because of course 5 times c is just a constant. Now here's where it gets a little bit tricky, not so much on this very first example, but because we have properties of logarithms, it's possible that the 5 could come up as an exponent. So when you're checking answers in the back of the book on some of the odd number problems that you practice, be aware of the fact that with natural logs comes the ability to expand or condense using the properties of logarithms. Now this one is a little bit more like the second rule, in that this part right here is going to be my u. If I let u be 2x minus 5, then that means that du would be the derivative of 2x minus 5, which is 2 dx. Now I have the dx sitting up top. I don't have the 2, but I can do that. I'll just grab my green pencil here. I'll put a 2 here that's times it, and then I'll put a 1/2 out in front to balance it out. So I have adjusted my constant, and I'm not making my substitution. I know where my u and my du. This is all my du. This is my u. So this is 1 over u du, sometimes referred to as a du over u form. So this is my du over u. So this is going to equal 1/2 the natural log of the absolute value of 2x minus 5, all that, plus c. That was pretty easy. This next one is much more difficult. Now, if you look at this and you say, well, how do I know, besides the fact that you're doing problems in section 5.2, how do I know I'm going to use the natural log, or the logarithmic rule for integration? Well, what you got to do here is you kind of look at it and say, all right, what form does it fit? And this does not fit a u to the n du, and there are no trig functions or anything along those lines. So I'm thinking that if it's going to work with this big expression in the denominator, I'm going to see if it's the du over u. So if this is my u, if u is equal to x squared plus 2x plus 5, then du would be the derivative of that. That would be 2x plus 2, all that dx. And even though I don't have 2x plus 2 dx, I have pretty much all that I need, because we can think of 2 times 2x plus 2 as 2 times x plus 1 dx. And all I need to do is, just like in the last problem, I just need to finagle my constant here by multiplying by 2 and multiplying by 1/2. So now I'm going to get 1/2 the natural log of the absolute value of x squared plus 2x plus 5, plus a constant. Now, this is my u, this is my du. It's 1/2 the natural log of u plus c. Now, here's again an example where they might have something a little different in the back of the book. What they may do here is, because first off, the expression x squared plus 2x plus 5 is non-negative. This expression is always greater than or equal to 0. I mean, if you set it greater than or equal to 0, greater than 0, let's say, not equal to 0, greater than 0, you will see that it's true for all real numbers. Remember that x squared plus 2x plus 5 can also be thought of as the quantity x plus 1 quantity squared plus 4. And that's always positive, or worth 0, and plus 4 that's going to make it positive. So I don't need absolute value bars there. I could write this as 1/2 the natural log of the quantity x squared plus 2x plus 5, because again, the stuff inside the parentheses is always greater than 0. And then on top of that, I could do the little trick by taking the exponent out in front, bringing it up here, or the constant out in front, bringing it up here as an exponent. So then all of a sudden I have the natural log of this expression to the 1/2, or the square root of x squared plus 2x plus 5 plus a constant. So if you're doing a multiple choice problem, you get this as an answer and it's not listed, you've got to investigate the possibilities that maybe it's simplified in some way, or maybe they used the property of logarithms. Be aware of that. All right, my next example is actually finding the area under a curve. So find the area of the region bounded by the graphs of y equals x over x squared plus 2, the x-axis, and the vertical line x equals 2. Now, you don't have to. I just have found it to be so much simpler if I do. I make a quick sketch. Doesn't have to be perfect. Just need something close enough that I can see what's going on here. So here's 1, here's 2. And if I put 0 in here, I get 0. Right? If I put 1 in here, I get a third. Let's see. I'll set up 1, 2 this way. So a third would be about here. And then if I plug 2 in, I get 2 over 6, which is also a third. I don't know, I'm probably just guessing. Probably something like this. Grab my graphing calculator. Let's make sure. So I turn that on. I go ahead to, of course, if I was really prepared, I'd have this already programmed in my calculator. Doggone me not being properly prepared here. Let's see. And what is that? Plus 2. And let's get a decent window here. We'll go from -2 to 4. Let's see. Negative. Yeah, this is not too bad. This is left over from the last video. Let's go ahead and see what this looks like. And about what I had. It comes up and goes there. And of course, x equals 2 is right there. So this is my region. Here's the x-axis, x equals 2. And my curve here, well, y equals x over x squared plus 2. So now I'm finding the area under the curve between 0 and 2, my x values, of my y value here, which is x over x squared plus 2 dx. Well, I will have to adjust my constant here. If I let u be x squared plus 2, then du would be 2x dx. So let's see, use the red pencil this time. I'll put a 2 in here, a 1/2 here. I'm not going to make my substitution, so I'm going to leave my limits of integration as is. This is equal to, now here's another denominator, x squared plus 2, my u. This is always non-negative. There's nothing you can plug in here that's going to make this 0 or a negative number. So what I'm going to do here is not use my absolute value bars. I'm going to write this as 1/2 the natural log of the quantity x squared plus 2 running from 0 to 2. So I'll substitute 2 in and I get 6. So I have 1/2 the natural log of 6 minus, plug 0 in. I'm going to have 1/2 the natural log of 2. Now this is not a terrible answer by any means. I can rewrite this. I can pop out the half. Write this as the natural log of 6 minus the natural log of 2, which of course is 1/2 the natural log of 3, 6 divided by 2. And then 1/2 would be an exponent, so this would be the natural log of the square root of 3. But since it's asking for the area, more than likely they're going to ask you to round it to 3 decimal places or something like this. I could leave it like this, and this of course is square units because it's area, but I could go ahead just as easily. Let me grab my calculator here and take the natural log of the square root of 3. that in and say that this is approximately 0.549 square units. This is kind of cool that you get an exact answer. I don't think I'd leave my answer expanded out like this. That was one of the reasons why we practiced some of the properties of logarithms, of condensing or expanding, to make it easier for situations as such. All right, so hopefully you can see that all right. Now, we have 3 examples down here. And what I want to do here is I want to see these problems. I see that I have a quotient, or what I've got written as the quotient form. I want to figure out how am I going to do this problem. So what I'm going to do here is I'm going to say, what's my u? And see if it works out that way. Well, my u in this problem would have to be x squared plus x. All right? So if my u is x squared plus x, my du would be 2x plus 1 dx. And it is all here. Let me grab another piece of paper here. Somewhere I've got some scratch paper, I hope. Maybe at the bottom here. There we go. So let me go ahead and finish this one off. It's all set up. This is going to be equal to here the natural log of the absolute value of x squared plus x, all that plus a constant. All right, the next example, I have the quotient form. If this is going to be a du over u, then my u would be the cotangent of x. And I have to be careful with these because with trig functions, we can put things in terms of sine and cosine and maybe rewrite it. But if u is the cotangent of x, I know that du is negative cosecant squared x dx. And this guy's ready to go. All I have to do is adjust my constant by putting a negative on the inside and a negative on the outside. So I'm going to get from here, this is going to be negative the natural log of the absolute value of the cotangent of x plus a constant. Now this guy here, he's a little bit more of a challenge. Not so bad, but a little bit more of a challenge. I'm going to let my u be the denominator, 2x squared plus 4x. My du then would be 4x plus 4, all that dx. So you can see here, I've got to adjust my constant by multiplying by 4 to get this, dx, and then a 1/4 on the outside. So this is going to be 1/4 the natural log of the absolute value of 2x squared plus 4x, all that plus c. So when you see that quotient form, be thinking about using the natural or the logarithmic rule for integration. All right. Now let's adjust this to a problem that looks more like this one, because these last examples, as I have mentioned here, they're pretty straightforward. It looks like a du over u when you first look at it, and then when you try your u and write your du, you can see that it is. But in this next example, my quotient form is not going to be so easy to set up because, first off, the degree of the numerator and the degree of the denominator are the same. So if the degree of the numerator is greater than or equal to the degree of the denominator, your first step is to divide. All right, because we can't use a du over u here. If your u, I'll bring it way over here, let's see if you can see this, is x squared plus 1, my du is 2x dx, and I have a whole lot more in my numerator than that. So I'm going to divide. I'm going to write 1, 1, 1, and negative 1. Oh, no, it's x squared plus 1. Oh, can't get away with that. Wishful thinking. Can't use synthetic division when I have x squared plus 1. So x squared plus x plus 1 divided by x squared, if it helps you, plus 0x plus 1. Put that placeholder in there. I need a 1. X squared plus 0x plus 1. Subtract or add the opposite, and I get x. So this x is going to be my remainder, so plus x all over x squared plus 1. And what I have now is an equivalent expression. I've just rewritten it by dividing, and now I'm going to try to integrate this. I'm going to break this apart into 2 integrals. I'm going to have 1 dx plus the integral of x over x squared plus 1 dx. Yeah, let's keep that scratch work over there. Now this is easy. I know how to integrate this. This is just going to be x. But I look at this, and this seems to fit the du over u. In fact, over here, remember the denominator is x squared plus 1. I would need a 2x dx I have the x and the dx. Grab my colored pencil here. I put a 2 here, a 1/2 here. You can see why I broke it up. And I now have the integral of dx is x plus 1/2 the natural log of the absolute value of x squared plus 1, but x squared plus 1 is always positive, so I don't need the absolute value bars, it's redundant, plus c, and I have my answer. You're going to need to know the logarithmic rule for integration. You're going to see it a bunch. Now, here's another one that's not quite as straightforward as some of the other examples that we've looked at. You have the integral of 3x all over x squared plus 1 quantity squared dx. Now, if I expand this and square this out, I would get x squared plus 2x plus 1. And you're not going to get your du over u here, because if you call this u, your du is going to be 2x plus 2 dx. That's not going to help us because I don't have that. So instead, I'm going to make a substitution. I'm going to change my variables. I'm going to let u equal the x plus 1 that's being squared, which means that du would be dx, but it would also mean that if I solve for x, x is equal to u minus 1. So look what happens now. I have the integral of 3x, so it would be 3 times that, 3 times the quantity u minus 1, all over u squared du, because your dx is your du. So now if I break this apart, in fact, I'll just pop the 3 out in front. If I break this apart, I get 3, the integral, I'm going to have u over u squared minus 1 over u squared du, which is 1 over u minus, and I'm going to write this as u to the negative 2 du. If I break this apart, this would be the integral of 1 over u du minus the integral of u to the negative 2 du. All that. This is the natural log, and this, of course, is the power rule. So this is going to give me the natural log of the absolute value of u, but of course my u here is x plus 1, so I have to have the absolute value because that can be negative. So I have 3 times the natural log of the absolute value of x plus 1, all right, minus, and then 3. This is going to go up to negative 1 over negative 1, so that's going to make it a plus 3, the quantity x plus 1 to the negative 1. I went ahead and substituted back in, plus c, which I'm going to write as 3, the natural log of the absolute value of x plus 1, plus 3 all over x plus 1, plus c. Now, I know if you looked at this and you said, I would have never thought to do this, well, that's why you've seen an example of it, so that you can be aware of the different kinds of approaches to these problems. See, when you differentiate, you can take the derivative of just about everything because the derivative rules include products and quotients and such. But integrating, it's a little bit trickier. You have to make sure that everything is set up right. So I've got a list of things to consider. When integrating, quote, a disguised integrand, when you couldn't tell right off the bat how to approach this, we need to rewrite it so that it fits one or more of the integration formulas. In this case, to rewrite it, I had to use a change of substitutions. You need to know your rules for integration. There's a whole long list of them. I believe it's in section 5 of this chapter. And so we'll get to that. So you need to know your basic list of integration formulas. If you don't already have them memorized, you're hurting yourself. You need to start memorizing them. Okay, so you find an integration formula that resembles all or part of the integrand, and sometimes by trial and error, you pick a u that fits and makes it conform to the formula. Now, if you can't find a substitution that works, you can try altering the integrand. Now, that's what I did here because I ended up dividing. You can also maybe have to use a trig identity so that you get an equivalent expression. Or sometimes you have to add or subtract the same quantity. Notice here, be creative. And when all else fails, plug it into your TI-89 and it'll do all the work for you. If it's integrable, it'll find that integral for you. Now here's the differential equations, kind of a cool looking problem. When we solve differential equations, we really only have one approach to solving those, and that is to separate the variables. So to separate the variables, I have all my x's on the right side with the dx, so I'm going to write this in terms of differentials. I'm going to write this as dy equals 1 over x natural log of x dx. And I'm going to integrate both sides. To integrate the left side is easy. To integrate the right side, it doesn't really fit a form right now. I mean, I'm looking at this. I have a natural log in the denominator, and I have an x in the denominator. You have to kind of play around with this. Now, since the natural log of x is kind of the bigger expression in terms of just a factor of x, if this was my u, my du would be 1 over x dx. Well, I have an x in the denominator. I could bring it up to the numerator and write it as 1 over x all over the natural log of x dx. By bringing, it's like you divide top and bottom by x. I have that now where that's my du. There's my du. So I have du over u. And I'm going to use the logarithmic differentiation here. So this is going to be integration here. So I'm going to get y equals the natural log. I don't think I'm going to write equals here. I'm going to just run out of space down here. Y equals the integral of dy is y. And this is going to be the natural log of u, which is the absolute value of the natural log of x plus c. So that looks kind of weird. I don't know if you've ever seen an expression where the natural log of a natural log, but we have to have the absolute values as well. Kind of weird. Now, this problem here, I mean, we do know how to find the derivative of the tangent of x, but we don't have one for the integral of the tangent of x. And that's a little tricky at first until you start thinking about what the tangent of x is. I make a substitution and I rewrite this as the sine of x over the cosine of x dx. So if I look at my quotient of form here and I let u equal the cosine of x, then my du is negative sine x dx, and I have most of that right there. I have the sine x and the dx. I just need the negative. So I take care of that, and I'm going to bring it over here to the left a little bit. This is going to be the opposite of the natural log of the absolute value of u, cosine of x, all that plus c. So we have an integration rule for the tangent of x. And as it turns out, we have one for the cotangent of x, which I have listed down here. Which, yeah, you should be able to see that. Now the next one here, don't cheat and look down below. Let me cover that up. The integral of the secant of x dx. Now that's 1 over cosine of x, but that's not going to be a du over u. 1 over the cosine of x is just not going to cut it. So I can't really use this as a du over u. So instead, what I'm going to think of is I'm going to, don't look. I'm going to look at this as the secant of x, and I'm going to multiply top and bottom by the same number. Like I can multiply top and bottom by 5. This is like secant of x over 1, if that helps you. Top and bottom by 5 or top and bottom by 10. I haven't put the dx in there. I'm going to put it on the end. I am going to multiply top and bottom by, you ready? The secant of x plus the tangent of x. Yeah, I know that's what you were thinking the whole time. Multiply top and bottom by the secant of x plus the tangent of x. So this gives me, up top, if I distribute, secant squared x plus secant x tangent x. And on the bottom, I have the secant of x plus the tangent of x. All that dx. Believe it or not, this is a du over u. If you let your u be the denominator, the secant of x plus the tangent of x, your du would be the derivative of that. Now the derivative of the secant of x is the secant of x tangent of x, and the derivative of tangent of x is secant squared x dx. Hopefully you can still see that. It's kind of sloppy. Do you see I have it all there? It's all there. It's just written in, commuted. So this is a du over u, and I get the natural log of the absolute value of the u, the denominator, plus c. And now you see why I have it covered up, because there it is. There's your rule right there. Here are the integrals for the 6 basic trig functions here. We already knew the first two. We had those earlier on, but here's now for tangent and cotangent. Now notice how similar they are. This is negative natural log of the absolute value of the cosine of u plus a constant. For a cotangent, it's natural log of the absolute value of the sine of u plus a constant. Look over here. The integral for secant u du is the natural log of the absolute value of secant u plus tangent u, all that plus c. And for cosecant u du, opposite, natural log of the absolute value of cosecant u plus cotangent u. So you see the secant is there and there's tangent. The cosecant is here and there's its cotangent. You can see how similar these are patterns to remember, so it makes it easier to memorize because you will need to memorize those. Now, let's try an example of a problem here. I want to do a definite integral from 0 to pi over 4 of the square root of 1 plus tangent squared x dx. Now, as it stands right here, I'm sunk. I don't have a clue on how to integrate the square root of 1 plus tangent squared x. This does not look like a du over u or a du over u or any kind of trig one. So what I have to do instead is I have to think, how can I rewrite this and make it look like something I know? Well, goes back to your pre-calculus days. 1 plus tangent squared x is equal to secant squared x. So this radicand is actually equivalent to secant squared x. Now look right here. We're going from 0 to pi over 4, so that's the first quadrant. All trig functions are positive in the first quadrant. So if I take the square root, make the substitution, and take the square root of this quantity squared, I don't need plus or minus because I know it's going to be positive here. So I'm just going to have from 0 to pi over 4 of the secant of x dx. Well, we just did that just a minute ago. This is equal to the natural log of the absolute value of the secant of x plus the tangent of x running from 0 to pi over 4. So if I plug pi over 4 in, I get the natural log of the absolute value of the secant of pi over 4 plus the tangent of pi over 4 minus the natural log of the absolute value of the secant of 0 plus the tangent of 0. Now, you may know your tangents a little bit, but I doubt if you know your secants, but they are the reciprocals of cosine. The cosine of pi over 4 is the square root of 2 over 2. The secant of pi over 4 is the square root of 2. The tangent of pi over 4 is the sine of pi over 4 over the cosine of pi over 4. So that's going to be square root 2 over 2 over square root 2 over 2, which is 1. Don't need the absolute value bars, that's for sure. Minus, now over here, the secant of 0 is 1 over the cosine of 0, which is 1, plus the tangent of 0 is the sine of 0 over the cosine of 0, which is 0. So I have here the natural log of the quantity, the square root of 2 plus 1, minus the natural log of 1, which is 0. The natural log of 1 is 0, so my answer is the natural log of the quantity of the square root of 2 plus 1. So that was a cute little problem there. All right, the only way you're going to get better at this, you probably already know it because I say it almost in every video, is to practice, practice, practice.